Hey everyone, and welcome. Today, we are putting together the ultimate study guide for a topic that, believe me, trips up even the pros: numerical errors. We tend to think of computers as these flawless math wizards, right? But what if I told you they can get it wrong? We're about to unravel the really fascinating reasons why.
So here's our game plan. First, we'll look at some head-scratching examples where computers just fail at basic math. Then, we're going on a little detective mission to uncover the main culprit: how computers actually store numbers. After that, we'll meet the two partners in crime, the types of errors they cause, and we'll check out the algorithms that fight back. And we'll wrap it all up with a handy cheat sheet to make sure all these key ideas really stick.
All right, let's dive right in. Our first stop is this central mystery. Why do these machines, built for perfect precision, sometimes give us answers that are just plain wrong?
Okay, let's start with a classic little puzzle. Take a look at this bit of code. It looks super simple, right? We start a variable, x, at 0, and we just keep adding 0.1 to it over and over until it equals exactly 1.0. You'd expect that to run 10 times and then poof, it stops.
Well, guess what? It never stops. This simple code creates an infinite loop. The condition, x is not equal to 1.0, is somehow always true. How is that even possible? How can adding 0.1 to itself 10 times not equal 1? Keep that question in your head because things are about to get even stranger.
Now look at this real-world example. Someone used a super complex 14th-order Taylor polynomial, that's some serious math, to calculate the sign of a number. And sure, the absolute error, the raw difference, was teeny tiny, but the final answer, it had the completely wrong sign and a massive relative error. The result wasn't just a little bit off, it was spectacularly, catastrophically wrong.
So the answer to both of these bizarre cases isn't some bug in the code. Oh no, it's much deeper than that. It's a fundamental feature of how computers represent numbers in the first place.
And the culprit has a name: the floating point number. This is the standard way that pretty much all computers handle numbers with decimal points. The key words here are fixed number of digits. See, the world of mathematics is infinite, but a computer's memory is very, very finite, and that's exactly where all the trouble starts.
So how does this work? Well, a floating point number gets broken down into three little pieces. First, you've got a sign bit. Is it positive or negative? Easy enough. Second, you have the mantissa. This part holds the actual digits of your number. You can think of it as the what. And finally, you have the exponent, which tells you where the decimal point goes. It's the where.
Now, there are two common flavors. Single precision uses 4 bytes of memory, which gets you about 7 significant decimal digits. The one you'll see most often is double precision. It uses 8 bytes and gives you around 15 significant digits. Now that sounds like a lot, but it is not infinite, and this brings us right back to our infinite loop. The number 0.1 in binary is like the fraction 1/3 in decimal. It's a repeating fraction that goes on forever. So the computer has to chop it off, which introduces a microscopic error that builds up every single time we go through that loop.
These limitations in the hardware itself give rise to two main types of error. These are our two accomplices in the mystery of bad math. And it's really, really important to understand the difference between them.
First on our list is truncation error. You can think of this as a shortcut error. It happens whenever we decide to approximate an infinite process with a finite one. That Taylor polynomial we mentioned earlier, it's an infinite series, but we only used the first 14 terms. We truncated the rest, and the part we chopped off is the truncation error.
And second, we have round-off error. This is a storage error. It's the error that exists simply because you can't stuff an infinitely precise number into a finite box. It's a direct result of that floating point system we just talked about. It's not a shortcut in your code, it's a fundamental limit of the machine itself.
So just to be crystal clear, these are not the same thing at all. Truncation error comes from your algorithm's design, the shortcuts you take. You can usually make it smaller by doing more work. Round-off error, on the other hand, is just baked into the hardware because of how numbers are stored.
And here's the really tricky part. These two errors are often in a tug of war. For example, if you're calculating a derivative numerically, using a smaller step size, h, will reduce your truncation error. That's good. But if you make h too small, you end up subtracting two numbers that are almost identical, which can cause your round-off error to absolutely explode.
And that explosion has a name that's as dramatic as it sounds: catastrophic cancellation. This is one of the biggest gotchas in all of numerical computing. When you subtract two numbers that are nearly equal, all those tiny little round-off errors they were already carrying suddenly get magnified, leading to a huge relative error in your tiny little result.
Our source text explains it perfectly. If you have two numbers, a and b,
and they're really, really close, their difference is going to be close to 0. So, any tiny little fuzziness in A or B can become a massive chunk of the final answer. You're left with an answer that is mostly noise.
But here's the cool part. We can be clever and avoid this. Look at the formula 1 minus cos x. When x is a very small number, cos x is super close to 1, so this subtraction is a recipe for disaster. However, with a little trig identity magic, we can rewrite it into a mathematically identical form, 2 sine squared of x over 2. This version completely avoids subtracting nearly equal numbers, and it gives a much more accurate result.
So if trying to calculate things directly is so full of traps, how do we solve complex problems accurately? Well, we bring in the heroes of our story, iterative algorithms. And when we have a hero, we need a way to measure just how fast and powerful they really are.
The basic idea here is really elegant. Instead of trying to find the answer in one giant leap, an iterative algorithm starts with an initial guess. Any guess will do sometimes, and then it applies a process over and over and over to make that guess better. With each loop, each iteration, we hopefully get a little bit closer to the true answer. The big question is, how much closer?
And we measure that using something called convergence rates. An algorithm with linear convergence is steady, it's predictable, it adds a constant number of correct digits with each step. But an algorithm with quadratic convergence? Oh, that's the superstar. It roughly doubles the number of correct digits with every single step. After just a few runs, you can get an answer that is ridiculously accurate.
All right, we have covered a ton of ground. We've seen the problem, we've unmasked the culprits, and we've met the heroes. So now, let's pull all of that together into a single, straightforward cheat sheet, perfect for review. So here are the absolute essentials. Floating point, that's the computer's finite way of storing real numbers. This system leads to 2 main errors. Truncation error is the shortcut error from stopping an infinite process. Round-off error is the storage error from that finite precision. The big danger to watch out for is catastrophic cancellation, that huge loss of precision when you subtract close numbers. And finally, when we fight back with algorithms, linear convergence gives us steady progress, while the amazing quadratic convergence doubles our accurate digits with every step.
And that leaves us with one final thought to chew on. We have seen that an algorithm with quadratic convergence is unbelievably fast. So it's a no-brainer, right? You should always pick that one. But is speed the only thing that matters? What about other factors, like stability, or how much work it takes to set up? Is the fastest algorithm truly always the best choice? Something to think about. Thanks for joining me on this deep dive.